I look at the current of the capacitor. Well, what's it equal to? What is that? It's a first order derivative. Uh-oh, no more mesh, no more node. And if you look at inductors, and you look at Faraday's law, you get that. No more node, no more mesh for inductors. So that means, remember that technique that I was trying to drive as hard as I can, called simple circuits with KCL and KVL? That's the name of the game. And you know why people hate it? Oh, because you gotta think. Man, that sucks, I agree. Okay, now that we're done with the sob story, let's move on. Okay. Seven. So now we're talking about energy storage elements. Capacitors and inductors are called storage elements. Why? Because a capacitor does what? What does it store? You could say electrical energy. I mean, but the main thing that we care about is the voltage across the cap. And I'm assuming that from Physics 4B, you understand what we mean by current through a capacitor. Capacitors are amazing. There's so much depth in capacitors. Sometimes I say, like, I know what a capacitor is doing, and then I go like, shit, I don't know anything about capacitors. I mean, there's just so much stuff in capacitors. They're freaking awesome. I mean, not to mention inductors. I mean, they're the equivalent of the other ones. So here we talk about storage of energy, electrical energy. Here we have a storage of what kind of energy? Magnetic energy. And what we mean by that is that if I have a charge across the two plates, there is a field, and a field has an energy density between these two plates. So you are essentially tapping this energy to move to different parts of the circuit here. An inductor, what does it do? It stores current, right? I mean, I'm sure you probably have shorted out capacitors. I don't know if you've ever gotten zapped by a capacitor, right? They can be quite dangerous. Inductors. Have you ever shorted out the big inductors downstairs in the lab? Oh man. Yeah, don't short those guys out. Now, I remember, you know, I was telling people when we were doing this inductor lab, this is what you don't want to do, right? And I was showing them how you have a fully saturated inductor, the big ones, right? The L value, that's a big ass value. And, you know, I'm telling them what not to do, and this guy goes like, what? Then all of a sudden he does it and he goes, so what do you think I called him? A dumbass. Why the hell did you do that? I'm telling you not to do that. And yet this dumbass does it, and I could show you how to do that. I'm sure you've been zapped by the Van de Graaff. There's no comparison. There's no comparison. But that's what we mean when we're talking about storage elements, right? We're talking about storage elements that do that here. So what we want to do here is that, let's start off with capacitors. So physically, what I want to do here is that I want to go in and I want to start and physically making sure that you physically understand. Why do we physically want to understand it now? Because when you get into chapter 8 and 9, you're going to be sweating about the equations that are coming at you now. So you're going to blank out for a while as we start going through all those details, especially when you get to chapter 9. Chapter 9 is the one you want to worry about. Okay? So intuitively, you got to understand that. So when you look at the circuit, you got to interpret what's going on. And you're going to see that there's some discontinuities in capacitors and inductors. And it's kind of surprising. And you can actually see that in PSpice. You can't see it in the lab so much because it happens typically like that. It's an instantaneous change. And so there's a discontinuities that you'll have to worry about. So that's what I mean that you want to pay attention. You're going to see that in circuits that have capacitors and inductors, this is where the discontinuity is like greatest. So let's look at these things here. So one of the things that I want to sort of look at this guy here, I'm just going to set up a very simple circuit with the switch. And for now, let's imagine that we have capacitors that are parallel plate. Why do we use parallel plate so much? Because they're easy to interpret. That's why. Do we have to use parallel capacitors? No. So when you start to look at this guy here, we imagine here that if I have a source here, I'm going to throw the switch, but we imagine that we start that it's uncharged. So if it's uncharged, then that means when I close my switch here, what's going to happen? I'm going to get current that starts to flow. Now, let's be realistic about these things. What do I mean by current flow in the circuit? I mean this. I close this switch, and as I close this switch, note that if this is ground right here, what we find here is that there's a voltage difference between, bad word, potential difference between the plates of the capacitor and the source. So now I get current that starts to flow. So as current starts to flow, what you're seeing here is that there's a potential change between Vs and the cap. Okay? So what happens here is that if I look at this plate right here, then that means if we use the standard model for current flow, that means I'm getting positive charge to flow onto this plate. Now, when I think about caps, what do I know about caps here? We have an insulator. Now, just to tell you how beautiful capacitors are, think about the following thing here. If charge is flowing onto this plate, does that mean that the electric field across the capacitor is changing? Yes. And if the electric field is changing, every time you have an electric field that's changing, you must be producing what? A magnetic field. So there is a magnetic field that's being set up along that. But wait a minute. If I have a magnetic field, I must have what? A current. And you'll see that there has to be some current going across this insulator. That's not a physical charge that's going through it, right? It's an insulator. If you have charge that's going through that, that's a bad thing because that means you've dielectric broke down the insulator through this material. So you can see that there's a lot here. And I think that I love capacitors. I think they're so interesting. By the way, I love inductors just as much. So when you're looking at this thing here, I build up charge here, right? So I build up charge here. So what do I do when I build up charge? Okay. But to do that, if I have an insulator, I gotta do what? I gotta polarize the insulator. And as I polarize the insulator, what do I do? I have this type of thing here, but if the field, if the charge coming on this thing, note I'm only saying that charge is coming in one direction, as we should say here, then that means that the positive charge on the lower plate must be what? Pushed away. So now I build up this negative charge Because why? I'm pushing positive charge away from the circuit. So what I mean by a current in the capacitor here is that I get a current, and then by induction and polarization, I push charge away from the bottom plate, so then I have this capacitor. And this guy continues to charge until, so we say that the cap charges up until the voltage of the source is equal to the voltage of the cap. And when that happens here, this implies here that the current in the circuit is zero. Okay, so that's what I mean by current flow through a capacitor here. So one of the things that we find here is that we could sort of like summarize when there is a potential difference between these two, then the current in the circuit is not zero. When these two are equal to each other, then that implies that the current is zero. And so this means here that typically we call this phase charging up, and this phase here that it's charged. We say that it's fully charged. That's what we mean by the pictures that we've been talking about here. And the way we typically, define these capacitors here is we typically use the capacitance equation. And the capacitance equation is typically written something like that. And when we look at this capacitance equation, what we see here is that the units of capacitance are farads, which we typically write like that here. Now, let me tell you, a lot has changed over the years. I remember when I was, I think I was a freshman in college or something like that. It turns out that I got a job. I actually volunteered, they didn't pay me for it, to work in the stockroom at the University of Arizona. And some graduate student comes in and says, I need a 1 farad capacitor. So what did I do? I went to go look for one. They didn't exist, really. So it was a freaking joke. We're talking, what, 40 years ago? Yeah, you couldn't go to the store and just say, I want a 1 farad capacitor. Some guy brought in the other day to my physics 10 class, yeah, I got a 5 farad capacitor. And I just kind of started laughing because I was that dumbass that went looking for that 1 farad capacitor and couldn't find it here. So humans should not be dealing with 1 farad capacitors, right? Because if that number is really big, what you'll find out is that you can dial it breakdown quite easy with a fully charged one. And so we typically deal with micro and picofarads when we talk about caps. Now, what we need here is that what we have to talk about is that we know how to calculate the voltage of caps. Right? We really don't, you'll see in this course here that we do care about the capacitance. We don't really care about the current. The charge. We care about the voltage. And so what we find here is that to determine the current I see here, that means then I got to take the derivative of the charge. But if I take the derivative of the charge here, that means I'm taking the derivative of this guy here. And we already know that the voltage of the cap is changing as a function of time. So if it's changing as a function of time, then that means I have to have a non-zero current flow. Assuming that the capacitance is fixed here, this tells me here that it's really this guy here. Right? So the current has to be this guy right there. And this is an important equation. It's a major player for the rest of the semester. And you're going to see that this will take lots of forms here, but instead of calling this the capacitors, I call this the capacitor equation. So if I say ever the capacitor equation, I automatically mean this one right here. And this guy really tells us quite a bit about what happens in a circuit. We remember RC behavior. Right? If you remember RC behavior, what you're looking at is you're looking at the following thing here. If I have the voltage as a function of time here, what we know about a circuit here is that if we get this maximum value of the source here, that means when I am charging up, I expect that the current should be non-zero. That means when I'm looking at this capacitor and I have an increase in the current as it's actually happening here, what you're seeing here is that you get this guy that looks something like this. So what you're seeing here is that when I get to over here, what I'm seeing here is that the slope measures current. So when I look at this curve right here, right? I'm looking at this whole curve, and I'm just shading this to not really look, I'm not trying to calculate area or anything, but what you're seeing here is that if I look at this slope right here, this means that the capacitor has a high current at this point. So that means because I have a steep slope, that implies that I have a high current. And I'm sure you remember this from 4B here. And the reason why the current is so high is that when I look at that parallel plate, what is it? It's empty of charge. Right? It's like, you probably heard the theater analogy. People, once they open the doors, people rush in. It's easy to find seats in the theater. But as time goes over, what you're seeing here is that the slope is decreasing right here. So now that I have, that it's less steep here, that means that I have a low current at that spot. So the charging of the cap starts off quickly and then it decreases. So going back to that theater analogy, we say what? You open up the doors to the theater and maybe it's a big release. I don't know. I don't go to the theaters very often. And then you see people rush in to get seats. But over time, people have taken up the spots in the theater, so what has to happen? The slope then must decrease. And as it decreases, that means it's harder and harder to find those seats here. Now, physically, there's a lot of ways that we can look at this thing here. You can imagine here that if I'm already putting positive charge onto this plate, the battery has to work harder, right? The charges have to work harder. Because as I come in, the positive charges are already repelling these charges. And one of the best capacitors that you can possibly work with is the Van de Graaff. Right? A Van de Graaff is a spherical capacitor. And you can hear when this is happening. Because when you have charge flowing onto the Van de Graaff, what you'll hear here is that the motor is moving very fast, and then suddenly what happens? You could hear it working harder. Well, that's because, effectively, there's less space for charges to find. There's this charge repulsion that's actually going, and this is where the Van de Graaff has to work harder to get those charges on there. But it's harder to get, so the current goes lower automatically. And so what we're seeing here is that that's what we mean by a capacitor here. And you'll find here, damn, I guess I overfilled this quite a bit, that to fully charge, we typically set a time of 5 time constants. And 5 time constants is really what, about 99%. So, I mean, I don't know what you did in your Physics 4A lab, but Physics 4B lab, where you looked at capacitors. I don't know if you did one where you just let a capacitor just fully, try to get to fully charged. To get this last little bit, it takes a while. And you'll see that in the lab, even though it gets to 99% of the voltage in, let's say, microseconds, I mean, to wait for this guy to get fully charged, I mean, you could go to time constants of, let's say, like 30, and you'll see that it's actually still not at its maximum voltage. So you'll see that to get to here takes a significant amount of time. So what you'll find here is that we should probably talk about, let's just talk about one thing before you, no, not the exams. Hey, I have grades. I won't be able to show them to you, but you can always come in and see the exam, your grade. In lab, I should have